The Firth of Forth rises beneath a morning mist, its iron bridge spanning the deep waters like a great beast frozen in time. Ship after ship glides beneath its expansive arches, mere phantoms against the colossal steelwork overhead. Trains rumble across the great cantilever structure, their weight pressing down upon its expertly engineered framework. As the sun rises higher, shadows play along the surface of the bridge, but something appears amiss. Look closely, and you may notice its center, gently rising into an elegant curve, its design deliberately crafted as a variation from the horizontal plane. Why, one might wonder, would engineers build such an imposing structure with a noticeable hump in the middle? How does this peculiar feature actually serve a purpose, and more importantly, what could possibly justify its existence in a structure designed for heavy steel locomotives and passenger trains? It's a puzzle waiting to be unveiled, a desperate need to understand how the laws of physics interact with engineering principles to create something seemingly odd yet astonishingly vital. As we delve into the mechanics of these magnificent railway bridges, we will explore the answer to the question. The engineering enigma lies in the way these giants are created for function, safety, and durability, while embracing the mysteries of stress, materials, and load distribution. To grasp this concept, we must first explore the fundamentals of engineering design, specifically how dead loads, the permanent weight of the structure itself, impact its performance under various conditions. When trains traverse the steel networks of long-span bridges, they exert tremendous pressure on their structures. For example, a standard freight train can weigh up to 4,000 tons. Now, add the factor of multiple cars combined with the weight of the bridge itself, and the total force can be staggering. Let's think of this force conceptually. Imagine dragging a heel downhill on a carpet. Your foot pushes the fabric down, compressing it while trying to maintain stability. This battle against gravity and motion is the same principle that a bridge undergoes. In a state of being unaltered, the bridge without any camber risks succumbing to the downward pull exerted by such immense loads. Engineers understand that as the forces exerted upon the bridge increase, a structure designed flat would result in considerable deflection, meaning the span would sag below the intended safe grade for railways. A flat surface would be inadequate because when a train passes over it, the structure bends under the weight, rendering it unsafe and unreliable. To mitigate this issue, engineers incorporate a purposeful upward curve or camber into the design during fabrication, a technique perfected over time. In the case of the Firth of Forth Bridge, which stands at a length of 2,538 meters and spans a main section of 1,600 meters, a camber of about 300 millimeters is of critical importance. Without this built-in deflection, once the bridge experiences the maximum load, it would sag beyond safety standards, which dictate that any rail line must maintain a minimum height of 400 millimeters above the water. So how exactly does this work? Here's the trick. By intentionally constructing the bridge with a camber upwards, the dead load deflection will ensure that once the structure is loaded, it flexes into a position that maintains the height required for safe rail operation. The bridge, when fully loaded, settles evenly into its designed profile, allowing for perfect alignment with the rail grade. Let's take a moment to consider another example. In the late 20th century, the Akashi Kaikyo Bridge in Japan, renowned for its astonishing span of over 1,921 meters, utilized similar principles. Though not a railway bridge, this suspension bridge experiences extreme loads, particularly in seismic conditions. Its design was meticulously calculated to account for upward camber during the initial construction phase, ensuring that when loaded with its own weight and the forces of nature, it performs effectively without compromising structural integrity. So, what does this mean for the railways traversing these bridges? As long as the engineers are calculating the necessary camber, they help guarantee that both passengers and freight are transported safely and smoothly across the vast expanses. It's a delicate interplay of forces, understanding gravity, material properties, and engineering design united in harmony. This brings us to a common misconception. Many people assume that bridges should be built entirely flat. They might picture a level surface as the ideal scenario, thinking flat beams convey strength and stability. However, this belief overlooks the critical aspect of load deflection. By embracing a slight upward curve, designers can prepare for the very forces they expect the bridge to face, thus ensuring longevity and safety. Now that we've explored the curvature concept, consider this engagement question: which of these structures do you believe relies on camber the most? A colossal suspension bridge like the Golden Gate, a rigid cable-stayed bridge like the CN Tower, or the mighty arch of Sydney Harbour Bridge? Share your thoughts in the comments below. Through this exploration of engineering psychology, we come upon the lesson that heavy structures thrive on calculated imperfections, each curve and chamber intricately designed with loads in mind. Engineers align physical reality with mathematical precision, creating a harmony that keeps trains moving smoothly across spans of metal and cement. To build a railway bridge with a deliberate hump in the middle is to embrace logic wrapped in artistry, with safety and reliability cradled within its design. Remember, when observing these massive structures, there is a graceful purpose behind their outward display. Each arching line, every upward curve, speaks volumes of the thought and calculation involved in transforming a simple span of steel into a symbol of endurance that carries the thrum of locomotion. As we draw nearer to closing, it's crucial to reflect on the ingenuity that surrounds us in our engineered world. Bridges, much like other structures, factories, skyscrapers, ships, are designed with foresight to deal with the unexpected, tweaking perceptions of common sense into something truly extraordinary. The next time you cross a massive railway bridge and notice the gentle rise at its center, remember the invisible forces at work. Engineers have woven a delicate narrative of strength, stability, and perseverance into the fabric of a structure that many take for granted every day. The machines that move the modern world are stranger than they look. Subscribe, and we will take apart the next giant together. To further understand the concept of camber and why it is indispensable in railway bridge design, let us delve deeper into the physical principles at play. Consider the concept of force distribution and how it relates to both the material properties of the bridge and the loads it endures. The interaction of weight and deflection reveals the intricate engineering calculations essential for the longevity of these structures. When a train passes over a bridge, it exerts not just the static loads from its weight but also dynamic loads associated with movement and acceleration. Think of a massive freight train, which can reach lengths of over 300 meters while weighing around 4,000 tons. Imagine this moving mass striking the bridge at even just 20 miles per hour. The kinetic energy demands precision and foresight in design. Each axle bears significant force, and the bridge must handle this without buckling or sagging. The upward camber plays a key role in distributing these weights to enhance the bridge's resilience. Engineers express this dynamic load in terms of live load, which specifically refers to the force produced by vehicles or trains that travel over the bridge. For instance, the live load for heavy freight trains can be represented as a concentrated load across the bridge's span. To illustrate, when calculating the capacity of bridges like the Firth of Forth, engineers must design for scenarios where multiple trains cross simultaneously, which can involve stress assessments exceeding 1,400 tons on a single beam. An example closer to home is the 57-mile-long Baltimore and Ohio Railroad's Thomas Viaduct, built in the early 19th century using a series of arches rather than a flat beam. This design, which incorporated gentle curves, enabled the structure to resist dynamic loads effectively. With an impressive span of over 680 feet, engineers were cognizant of the camber that allowed the bridge to smoothly absorb the forces exerted by the trains above. The upward curvature served as a passive counterbalancing mechanism for deflection once the bridge received the additional weight. As we further examine camber, we begin to see its fundamental role in mitigating fatigue, an aspect often overlooked in structural engineering. Over time, all bridges experience wear due to the oscillating forces that occur when trains pass. Bridges are not static, they are dynamic structures that flex. Without the initial upward camber, the constant cycling of loads would amplify the sagging effect, leading to quicker structural degradation. In fact, one of the leading causes of bridge failures is fatigue, arising from repeated deflection cycles that weaken materials. This includes the failure of the famous Tacoma Narrows Bridge, which, although not a railway bridge, serves as an important cautionary tale regarding engineering perception. Built in the 1940s, its design was deemed overly elegant yet lacked sufficient damping mechanisms to manage oscillating effects. without a calculated understanding of how external forces acted upon it, in this case, wind, the bridge endured catastrophic failure. This incident highlights why maintaining shape through controlled design, such as with camber in railroad bridges, is vital in preserving functionality and safety. As we continue exploring the manifestations of camber, let us consider yet another specific example, the George C. Page Bridge, which loops over the Charlotte Harbor in Florida and epitomizes modern bridge design. This structure incorporates an upward camber of approximately 150 mm at its center. Engineers had to take into account various factors, such as climatic conditions, potential flood heights, and the heavy traffic expected to use it over its lifespan. What stands out in using this design is its ability to self-correct. When a heavy load passes, the structure's geometry induces a constant upward reaction, forcing the horizontal component inward, thus balancing external forces. In contrast, a flat bridge would complain under these weights, potentially developing dangerous torsional shifts. The hidden camber, often imperceptible to the passing observer, ensures the bridge retains its intended profile, even in severe conditions. The act of constructing bridges with this deliberate curve is a philosophical exploration in engineering, an interplay of art and science, intuition, and calculation. It harkens back to the rope bridges of the Inca civilization, where their upward arcs acted similarly, distributing forces through tension. Such ancient wisdom informs modern engineering principles that persist today, showcasing a continuous evolution of thought in structural integrity. Now consider the importance of material selection in this dialogue about camber. Modern railway bridges utilize high-strength steel that enables thinner and lighter designs while still retaining extraordinary strength. The Firth of Forth Bridge, completed in 1890, was a pioneering example, using wrought iron, a precursor to the steel alloys that dominate today's structures. Its innovative use of steel and careful consideration of upward camber allowed it to span distances previously thought impossible. With sections weighing upwards of 500 tons, this massive structure holds its shape against the elements while maintaining the necessary height for safe train passage beneath. Looking further into our discussion about longevity, let's explore the engineering principle known as redundancy. Redundancy in bridge engineering refers to the incorporation of multiple pathways for load to travel, which ensures that if one element were to fail, others could carry that weight. An excellent example of this principle can be observed in the Brooklyn Bridge, which employs a hybrid design made of both steel cable and granite towers, delivering dynamic capabilities to handle a multitude of pressures. The inclusion of camber works in synergy with redundancy. As loads pass, the upward curve aids not just in managing deflection but also in distributing stress across the multiple elements of the structure. But why stop here? The exploration of camber can traverse continents. In fact, in the Nordic regions, we observe similar engineering principles articulated in designs for the most adaptable bridges, like the Øresund Bridge connecting Sweden and Denmark. It features immense spans that rise gently, allowing vessels underneath enough clearance and maintaining rail lines perfectly aligned. Its design, balancing elegance and practicality, is a living nod to the centuries-old knowledge of camber resolution in bridge engineering. So let us return to our earlier premise regarding common misconceptions. As stated, people often believe that flat surfaces guarantee strength. Yet, we discover that they can easily overlook the intricacies of loading scenarios and material behavior. Engineers know that the natural forces of tension and compression through curvature are vital building blocks of sound engineering. By incorporating an upward camber, they prepare for and embrace the realities of weight, wear, and forces beyond simple static calculations. This slight but intentional bend in design offers a fascinating counternarrative to our expectations, calling into question preconceived notions of stability. As we surf through the nuances and technicalities of bridge design, let us take yet another moment to reflect on the balance achieved in these engineering marvels. The curves and humps present in designs are more than aesthetic choices, they are testament to human ingenuity. They encapsulate the struggle humans have had with understanding physics through the prism of design, forever seeking harmony with the forces of nature while facing the challenges brought forth by our unfolding industrial age. Consider this: each gargantuan bridge carries within it a secret, whispering of calculations, material science, and human ambition. When we look upon these grand structures, we see triumphs over gravity and time, reflecting our aspirations and principles encoded into their very foundations. As we conclude this profound journey through the engineering lens of Camber, let us remember that every structure is alive with the legacy of insight, an embodiment of knowledge restored through years of practice and advancement. Bridges like the Firth of Forth and modern counterparts exemplify the mastery of calculated form and function, where the delicate arc of upward camber is an icon of safety woven into the very fabric of our world. The machines that move